In this video, we're going to take a look at calculating the electronegativity of bonds within a molecule. In the previous video, we saw how do you calculate the electronegativity of a bond. So if I gave you a bond between Si and P, just what is that electronegativity going to be? But let's go ahead and draw some molecules and calculate the electronegativity of all the bonds within that molecule. Um, So we're going to start with some examples of nonpolar covalent bonds within molecules. Remember, for nonpolar covalent, you'd have to have an electronegativity difference of less than 0.5. And if you're exactly on 0, that's pure covalent, which means it's as equal of a share as you can get because the the atoms have the same electronegativity value. So let's start with Cl2. What I like to do is I like to draw a Lewis dot structure and calculate the electronegativity values. Um, so if we look over here, our delta En is going to be between two chlorine atoms because there's Cl2 there. So it's just 3.0 minus 3.0 is equal to 0. So we have a non-polar covalent bond, and better yet, it's actually a pure covalent bond. But we could just call it non-polar. It's a very equal share of electrons. And we can draw our Lewis structure like this, as we've seen in previous lessons. And that's essentially it. We calculated the electronegativity, the polarity of this bond here, and we found that it was non-polar, specifically pure polar. If we had found that there was a polar bond within a molecule, we would want to represent that polar bond with one of these arrows. So if you look at this arrow over here, the arrowhead points towards the more electronegative atom. That's a partial negative charge. And the arrow tail here with the positive sign there is near the atom that's less electronegative. So there's a partial positive charge on it. So if ever you have a bond that is polar, you need to put this arrow, and that arrow is called a dipole vector. It's pointing in the direction of the more electronegative atom and shows where the major pull is occurring. In our molecule that we drew up here, we had a nonpolar bond in there, so we don't have to draw a dipole vector to indicate a bond dipole. A bond dipole really just means that our bond has an unequal share of electron, unequal spread of electrons. The density is not really of electrons is not equal. You have more hanging out around the chlorine area than you do around the hydrogen area. But in this case, the density would be spread equally between the two chlorines. Let's take a look at the example of CH4. So let's draw out this molecule first to see what bonds are present. And so you would just use the regular rules we saw for Lewis structures. Check to make sure it is a covalent bond of some sort. And you'll notice there's actually 4 bonds here, but luckily they're all the same bonds. They're all CH bonds. And so let's calculate the electronegativity value, the electronegativity difference between C and H. So we have delta En is equal to 2.5 minus 2.1, and we get 0.4. So 0.4 is less than 0.5. Therefore, this is nonpolar covalent. It's still a share, and it's an equal share. Because it's nonpolar covalent, we don't need to draw one of those dipole vectors in there, since it's a roughly equal share of electrons. The electrons probably do hang out a little bit closer to the carbon because there is a slight difference in electronegativity, but for the purpose of this course, we assume that this is a roughly equal share, so no need to draw those dipole vectors. Now, let's go take a look at some molecules that contain polar covalent bonds. If you do see that, you do need to put the dipole vector, and we'll practice doing that. So remember that for polar covalent, you need to be 0.7 to less than 0.5 to less than 1.7. For example, HCl. So if we draw that out, let's just do our calculation here. We have delta En is equal to 3.0 minus 2.1. Because the electronegativity of chlorine is 3.0. And you can get that from your periodic table as we saw in the previous lesson. But just to show you again, if we go to our periodic table, chlorine is 3.0, hydrogen is 2.1, and so we get a difference in electronegativity of 0.9. 0.9 is more than 0.5, but it is less than 1.7. So this means that we have a polar covalent bond that exists in the HCl molecule. And again, I'm just drawing the Lewis dot structure as I would normally draw it out. And now I have to put my dipole vector. The arrow points towards the more electronegative atom, which is the chlorine, and it has a partial negative charge. And the hydrogen would therefore have a partial positive charge. It's not a full charge because the electron was not fully transferred. Let's try the same thing, but this time for HBr. So for HBr, same idea. We're going to do our delta electronegativity. So Br, if we look at our periodic table, is 2.8. So 2.8 minus 2.1, and we get 0.7. And so 0.7 is more than 0.5, but less than 1.7. So we have another example of a polar covalent bond in this molecule. And so we would have to draw out the dipole vector again, and you could predict where it's going to go towards a more electronegative atom, which is the Br. Make sure you put your partial negative and your partial positive. So those are some examples of bonds within molecules. So we found bonds within the Cl2 molecule was non-polar. There's only one bond there. We found that CH4 has 4 bonds, basically 4 CH bonds. And each of those bonds are going to be non-polar because we found that the difference between CNH is 0.4. And then we did other molecules that were polar, and we drew them out, and we found the difference. And we saw that they ended up being polar covalent bonds in there. And so we drew our arrows to show that. Let's try this one. So you can probably guess that this is going to be ionic. It might not be, but for the most part, when you see a metal and non-metal, you're going to have ionic. There are exceptions, though. And that's where you have delta En, electronegativity difference, that's 1.7 or more. And the electrons are shared so unequally that we assume that it's a full transfer. And so we get full charges as opposed to partial charges. So let's just calculate the delta En just to confirm that we have an ionic bond there. So Mg and O. So Mg is 1.2 and O is 3.5. So we have 3.5 minus 1.2, and we get 2.3. 2.3 is more than 1.7, therefore it's ionic. We don't draw dipole vectors because there's not partial charges, it's full charges. So what we would do is we would show our transfer of electrons happening, as you normally do when you're doing the Lewis structures for ionic compounds. And then you would show your full charges. And that would be all you need to do. You have full charges here. And as you know, this is magnesium oxide because there's one magnesium, one O, that's magnesium oxide. So what we focused on was essentially bond polarity within molecules. But what I need you to understand is that there's a difference between the bond polarity and the molecular polarity. Bond polarity means the polarity of a specific bond in that molecule. So for example, if I was looking here at this molecule here, I might ask you for the polarity of the various bonds. So the bond here, 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 here. And what you would have to do is you would have to calculate the electronegativity difference for each bond there. But that's not the same thing as molecular polarity. You might have some molecules with some polar bonds, some non-polar bonds, And overall, the molecule might be nonpolar, even though there's polar bonds there. You might have molecules with only polar bonds, and overall, the molecule might still be nonpolar, even though there's polar bonds there. So, molecular polarity is the overall polarity of the entire molecule. And so, again, just because you have a polar bond, it doesn't mean that you're going to have a polar molecule. You actually have to consider quite a few different aspects of the molecule. You need to consider the bonds in the molecule, so all the bonds that are there. And you also need to consider the shape or geometry of the molecule. So in our next video, we're going to take a look at how do we figure out if a molecule is actually polar or nonpolar based on all the bonds that it has and based on its shape and its geometry.